Okay, so now we are doing the W5, which is coagulation and flocculation, where we have the water samples that is put into beakers at 500 ml each, and these samples are from the same location, which is the outlet at the Unimas Lake near the boathouse, which is sample 1. Okay, and what we will be doing now is that for beaker A, we will use it as a control sample where we will just be adjusting the pH, and there will be no alum in it. Okay, beaker B, we will put in 5 ml of alum, where that will equate to 25 ppm, okay, parts per million. And then beaker C is 50 ppm, beaker D 75 ppm, and beaker E 100 ppm, and finally beaker F 125 ppm. So basically what we are trying to do here is that we are fixing the pH. We assume that the pH is optimum for the pH for the coagulation and flocculation process is optimized at 6.5, but we want to find out what is the optimum alum dosage to obtain the desired flocks, okay, before it flows into the sedimentation tank in the water treatment plant. Okay, so this is the alum, okay, that we have here. So 1 ml of alum that we put into the beaker will be equivalent to 5 parts per million. So as you can see here, if you look inside the beaker, okay, this one is in beaker A. Okay, you can observe the condition of the water sample, where you can see some solids that is already settled at the bottom, but there is also some solids that is still suspended, which is a lot finer than what you can see at the bottom of the beaker. Okay, so this is before we put in the alum. Okay, so for this one is in beaker B. Okay, so the similar condition, okay, as you can see here. This is beaker C. Okay, so just at the start of the experiment, before the jar test, okay, before we put in the alum, this one is beaker E already, okay, and this is beaker F. Okay, so condition is the same. Okay, so now we are going to put in the alum. So what we are going to do now is that we are going to put in the alum into the beaker. So each time is 5 ml, right? Okay. So this one would require 10 ml for beaker C. Okay, so I'll do it 2 times. So for beaker D, I'll do it 3 times. Okay, beaker E, I'll do it 4 times. Beaker F, I'll do it 5 times. Okay. Okay, so now what we are doing is for beaker A is to determine what is the initial pH. Okay, so which you can see here from the pH meter. Okay, so now what we're going to do is to lower the pH to the final pH of 6.5. So in order to do that, we need to add some acid in there. Okay. So what we want to do here is to add acid until we can bring it down the pH to 6.5. Okay, so now we are hitting around 6.5, so that is sufficient to we can take it as the final pH. Okay, this is for beaker B. Okay, we are now trying to measure the pH, initial pH. So this is for beaker C. Okay, so as you can see, as you add in more alum, your pH is actually going down. Okay, so this is at 50 parts per million of alum in the water sample. Okay, so it's going down to around 6.1. So having said that, we need to add sodium hydroxide to increase the pH to somewhere around 6.4 to 6.5. So this is after adding about slightly over 1 ml of sodium hydroxide. There's an increase by about 0.1 pH. So this is for beaker D. Okay. After putting in 75 parts per million of alum, so the pH has gone down to around 5. So this is for beaker E, 100 ppm. So the pH is going down to way below 5, about 4.6, 4.5 maybe. So this is the initial. Okay, so the pH is now 6.44, which is acceptable. 6.45. The pH is now 6.45, which is within the acceptable range.
6.
Right, so this is a pH for beaker F, initial pH before we do any adjustment. Okay, at 125 ppm. Okay, so as we can see here, we are now doing the coagulation phase. It's been almost 10 minutes. So this is for beaker A. Okay, so this is for beaker B, right? This is C and D. This is for E, okay, and this is for F. So what we are going to do now is to slow down the mixing speed to simulate the flocculation phase. Okay. Okay. So we need to have a high speed for coagulation phase in order to increase the frequency of collision between the colloids and also the alum to break down the negative charge barriers around the colloid particles. Okay, so now we are slowing down the mixing speed from 400 rpm to about 60 rpm. Okay, 400 rpm for 10 minutes and 60 rpm for about 20 minutes. Alright, so these are how the beakers, the water sample looks like after the coagulation and flocculation process. Okay, so what we will be seeing later on is after about half an hour of settling, how would the flocks, okay, look like, okay, or more so known as sludge, okay, formation of sludge after half an hour for it to settle. Okay, so this is how it looks like from the plan view, okay, for beaker A, beaker B, beaker C, beaker D, beaker F, sorry, beaker E, and beaker F. Okay, so what you can do is that you can stop the video to observe the flocks that is formed later on. These are the appearance of the beakers. Okay, the solution in the beakers after we are given ample time for it to settle. Okay, for the flocks to settle. So for jar test, normally what we do is that we look at a few things. We look at the water itself. Okay, I'm not sure whether you can see this or not. There's actually still for beaker A, because there's no alum that is being provided, so there's still some colloids that is settled. Sorry, they're still suspended, as you can see in here. I'm not sure whether it's clear enough or not. Okay, but what we see is that whether there's any thing that is floating or not, there's still some things that is floating, and then there are some things that is already settled at the bottom. So those are the more largest solids and particles. Yeah. Okay. Okay, so for beaker B, where we have put in 25 ppm of alum, so what happens here is that you can still see all these things that is floating here. All these are microflux. Okay, this microflux is not what we want, because microflux is formed during the coagulation process, and because there's insufficient alum that's been provided, so it's not able to agglomerate all the microflocks together, so that's why some of it are still floating. Okay, and as you can see here, even the flock formation, okay, the flock formation here is a bit fluffy, okay, because you do not have enough alum to neutralize the negative charge of the colloid particles. Okay, so for beaker C, you can see that there's less floatable microflocks, okay, and you can see that there's a formation of flocks that is already settled at the bottom here, okay. But if you look at the thickness of the flocks, okay, it's still relatively fluffy, okay, and you can see that it's later on that it's relatively thicker than any other beakers later on. Alright, you can still see that the flocks itself is a bit fluffy still. Right, so next we look at beaker D, which is 75 ppm. Right, so here you can see that there's significantly less floatables. I think this is from the room. Okay, there's on the surface here. Okay, but if you can see here that if you compare that with beaker C, the flocks here is actually finer, it's more well defined, it's not that fluffy. Alright, and if you look at the side here, okay, it's actually relatively thinner than beaker C. Here you can see that beaker C flocks are actually quite fluffy, and whereas beaker D on your right hand side is more defined. Okay, even you can see it from the color itself. Okay, so next, beaker E, you can see that the flocks that is formed compared to that in beaker D here is actually getting larger. Okay, there's probably because you're putting in a bit too much of alum, and now you have more positive charge alum inside to repel the in the flocks. Okay, but nevertheless you can see that the flocks formation is still defined. Okay, it's just that comparatively is fluffier than the one in beaker D. Okay, so the last one here is beaker F. Okay, so if you can see that the flocks here, it seems that is quite similar to beaker D. Okay, but then that's the reason why we cannot just base on the observation. For observation, there are a few things that we are looking at. First thing is the flock quality, whether it's well defined or not, or is fluffy. And second thing is the settling time. Okay, for the flocks, preferably is within half an hour. Okay, because for it to settle in the sedimentation tank, usually we give it about half an hour, but in the sedimentation tank design, we are talking about 1.5 to 2 hours hydraulic residence time. Okay, so the next thing we need to do is to check the turbidity of in each of these solutions. Okay, right, so in order to measure turbidity, what we use is the turbidity meter. Okay, this has been calibrated by Chagiza. So we're going to use it. How we're going to use it is that we have a valve here, which is about 10 mil. So there's a marking here. So after we fill it in with this water sample, then we just put it in here. So long as you fill it up to this marking here, then you should be able to do a reading. Right? So how we're going to do it is to use a pipette. Okay, this is a 10 mil pipette. Okay, so we need to push down the plunger first, and then submerge the tip below the water level, and then you take out the water sample. Okay, so you need to wipe it dry and clean, because this is using light, scattered lights to measure the turbidity. Okay, so for using a turbidity meter, you need to make sure that this point is pointed aligned with the arrow here. So this is for beaker F at 125 ppm. So this is for beaker E at 100 ppm. So this is for beaker D, 75 ppm. Right, this is for beaker C, 50 ppm. So this is for beaker B at 25 ppm. So this is from beaker A, which is the control sample without any element.